Iwan, I will talk in a second.
Okay, well, I should thank the organizers for allowing me to speak here, because unlike most of the speakers today, I never had the pleasure of actually working closely with Richard. However, we were the nearest neighbors for at least a decade. And so obviously in the corridors, I often ran into Richard or popped into his office from time to time and asked advice, or just to have a little chat. And I always found him extremely helpful, and his advice sage and very useful. So when I was asked to present a talk here, I thought I would have a look back through my archives of unpublished results and see if I could find something that related to work by Richard. And I ended up deciding that I would talk a little bit about osculating walkers. So as many of you know, Richard made some great contribution in this area on the connection to alternating sign matrices and some very complicated constant term expressions for the numbers and so on and so forth. So it's very impressive. So I also had a brief talk with Tony yesterday, on who actually came up with the term osculating paths. And he wasn't entirely sure, but he thought that calling him osculating probably too frivolous to be Richard. So he claimed that it was probably himself that came up with it. And but anyway, I first came across him and talked by Richard. So that's my connection. So as I reacquainted myself with these results that I will briefly talk about, and added a few more over the past couple of weeks, I found myself in sort of a very familiar situation for me, which is that I found that the more I know about a problem, the less I understand. And so I'm going to share some of the things that I know, and hopefully maybe some of you can help me understand it a bit better. So I'm going to talk about osculating walkers. So we're going to essentially consider, there'll be a picture on the next slide, a number of directed walkers on the square lattice. So each of these are essentially a directed walk or a big path, if you wish. And so we can only take steps in two directions, up or down, diagonally here. And we just have some labeling of them, of course, and there can be up to P of them. And all we need to do here to essentially look at this from the point of view that I wish to look at it for enumeration is just to keep track of the ordinates of the walkers. And so walkers are not allowed to cross, but they may share vertices. So if they're not allowed to cross, it's an even more general, or not general, but specialized problem, but much more well known, called vicious walkers. They're not allowed to touch at all. But for osculating walkers, they are allowed to share. They're not allowed to share an edge, but only a vertex. So they are allowed to meet fleetingly, but they must separate immediately. So all of these type problems are quite easy to enumerate. It says you have a polynomial time algorithm in the most trivial cases here of order into the p-1, because you only need to keep track of the gaps between the walkers, and it's just a polynomial type binomial number of these. So the generating functions, as it turns out here, are solutions of Fuchsian ODEs. So you've got the finite series. So this particular study here plays into one of the strands of things I like to do, which is essentially form an exact sequence, integer sequence, to try to find the generating functions numerically. So I don't want to talk much about that, just that the way to do that is modular arithmetic if you want to do it efficiently. So you calculate the integer coefficient, modular prime number, and then you look for some underlying equation that these sequences satisfy. In this case, a differential equation. Could be algebraic if you want to be simpler, or it could be d-algebraic if you want to be fancy. But in this case, it's just an ODE. And of course, once you have an ODE, you have all the heavy artillery that we learned in calculus, differential equations, of how to find singularities and critical exponents and so on and so forth. So here's an example of free osculating Walkers in what is called a star configuration. So in this case, they start at adjacent sites, especially over here on the left, but they can end at any site on the right after taking end steps. And because it's easy, I decided that I would have let's look at some slightly different boundary conditions here. For these boundary conditions over on the left here, with equidistance are appropriate for vicious walkers where you're not allowed to share vertices. But for oscillating walkers, you are allowed to share vertices, so you don't have to actually start them out. Separated like this, you could have them share a vertex. And of course, the constraint is you can only have 2 walkers per vertex at most. So for instance, if you had 4 walkers, as we will look at in a tick, you could have them start out 2 walkers here and 2 walkers there, and then form a star. That's permitted. So I distinguish between these 2 types of boundary conditions. This guy's called vicious, because that's the appropriate one for vicious walkers, as I said, and osculating when they are allowed to start at the same vertex in pairs. Okay, so it's very simple to see that the dominant physical singularities width is 1/2 to the 2p, 1/2 to p. Yeah, and the number of these are known by work from the audience members. This is where I lifted it from, as a simple product. And for osculating free stars with the vicious boundaries, we proved, okay, in a conference paper where we were honoring another great mathematician, Tony, on his 60th birthday. And she presented this result here for the generating function, as we see, very simple algebraic generating function for free osculating Walkers. So essentially, this is a summary of what happens if you go to 4 or 5 Walkers. So there's a number there. You can see here, of course, it becomes a little more complicated now. And essentially what happens is that, as you can see, the order of the differential equation increases to 5 if you have 4 Walkers. And we now have, okay, not just dominant singularity, but there's a number of non-physical ones as well. And this is just a list of what type of exponents we get. So here at the physical singularity, you can essentially solve the, it's called the initial equation. It gives us the possible singularities. And a repeated integer here means that you have a logarithmic singularity. So that's the case both for 4 and 5. And here's a bit I don't necessarily understand, why the osculating seems to be simpler when you start at an osculating boundary condition. You get essentially orders the same. So whether this is really simpler, we can always discuss that. That might be philosophical, but the degree of the polynomials that appear in the differential equation now decreases, and quite substantially, as you can see, certainly for 5 Walkers. So this might be an example. I mean, I don't quite understand this. I would have intuitively, and that's just shows you never rely on my intuition anyway, that the osculating boundary conditions where you're actually forcing, okay, two walkers to share and be next to each other here with 4 would be more constraining, and therefore you would have thought a tighter constraint might lead to more difficulties satisfying that. So, but anyway, get a simpler differential equation in a sense. So those are the singularities. We're going to go on and ask ourselves, to what extent can we actually solve this? And we can certainly make quite a bit of progress in that direction if someone was interested in a closed form, not just the differential equation, but actually write down here's an expression. This is what the generating function is. So I'll only talk about the 4 case. So the differential operator here, which is of order 5, now breaks down into essentially, let's say this is a sum decomposition to the product. Okay, Mabel do this reasonably efficiently for these sizes. So it breaks it down into a product of a order 1 and an order 4. So this is what is called sometimes a direct sum decomposition. What is in, if you are using Maple, it's a command d factor LCLM. So the nice thing about such a decomposition here, and the reason that it's interesting to look at, is that if you have a breakdown in an LCLM factorization, then what is the case is that the solutions of these operators are also solutions of the operator on the left here. So for instance, a solution here of L4 would also be a solution of L5, and similar for this L1. Now L4 further breaks down into a product factorization, 2 order 1s and then order 2, as is listed here. Now this is a standard factorization, so that means that, okay, solutions of N1, obviously because it's rightmost, is also are solutions of L4. But if you can find solutions of M1 and L2, as we can in this case, these are not solutions of L4, unfortunately. So it doesn't quite help us to find a closed form solution, but we're getting there. So here are the solutions. You can see very simple rational solution. And then some algebraic solutions here. And for L2, these are now solutions in terms of hypergeometric functions. And the probably shouldn't surprise us, because if one looks at the vicious stars, in fact, these are all of them, those that I've looked at so far, can be written solutions there. There was that product we had in the start. So since you have a product for the terms, it's not surprising really that hypergeometric solutions pop up. But for there, I think up to 8 or whatever I had looked at, as I look through my old papers or old archive there, can be written up to 7 in terms of F21s. So these are like these guys. And for 8, it actually comes in F32. But anyway, that's an aside. So, but of course, hypergeometric functions are so general that it's not necessarily very interesting. You can find a solution in terms of them, because it doesn't necessarily tell you all that much. So, five walkers. Next. Okay. We have an order 6. Breaks down here. again, this is LCLM decomposition, 2 order 1s and an order 4. Order 4 again breaks down as before. 1 of order 2 and 2 of order 1. And again, all of these operators, we can find the solutions. And there they are again, rational functions, a simple algebraic, and hypergeometric for L2. So that's stars. We're almost done. So we can get an early coffee break. The second problem one can look at here, as was already mentioned in Box's talk, of watermelon configurations. Okay, so walkers start and finish on neighboring sides, so that's the vicious configurations. And you can also, again, at the boundaries, put osculating ones if you wish. I did that. It's easy to generate the terms, it's easy to find the solutions. So the dominant thing is physical singularity again, 1 on 2 to the p, or critical exponents, alpha p there. Which brings me to one of the bold statements from Tony's talk, that there's no models. This has a critical exponents of 15. I don't know if 15 is among those numbers, but anyway. So here, again, sometimes you get into the values for the second time. And in that case, singularity is of a logarithmic type. So John Essam and Tony found a generating function for 3 vicious walkers and expressed it in terms of point functions. And for osculating 3 watermelons, you can express these in terms of the generating function for 3 vicious in that form. And okay, let's very briefly, final slide. So here again, okay, number of order, initial conditions, order of the differential equations, degrees, and so on and so forth of the polynomials that appear in these differential equations, the singularities. I don't want to list the exponents here. So in this case, it's a little more complicated, much bigger differential equations. We don't get as far yet. But there's a number of very simple solutions to this differential equation. In fact, there are 3 rational solutions for 4 walkers and 4 rational solutions for 5 walkers. So that's a start towards solving it explicitly. And for 4 osculating, this was what my laptop could handle. You can, with osculating boundary conditions, you can find this decomposition of the operator and find some simple solutions. So that's it for me. Okay. So.
Online questions? All silent from across the place inside the room.
So the only restriction for finding solution for vicious space is what the size of your enable.
Yes, in a sense, yes.
And presumably, do you think that the number of singularities and their location would be the same in space?
Yeah, no, I mean, no, these singularities are. Okay, so the question is whether or not the singularities in the business case, in fact, they're the same. I just didn't want to write them down twice. So these are the same singularities here, and the same exponent at the dominant singularity, at the physical singularity. There are some differences at the non-physical ones. Okay, so these are all.
ask, is this a typical thing that Bishop's models have such a
This is just boundary conditions, so I don't know why.
okay,
That's what I don't understand.
that's not generic.
I have no idea. I only studied it for this particular case. So, you can do friendly walkers, you can check out whether or not it's the same thing. I can do that. I mean, it's easy to do. It's a day's work to do it. So.
No other questions? Okay, thanks very much, Iwan.